Good afternoon. I'm Bob Aarons, host of the Friday Seminars. Thank you very much for showing up. This is a great turnout. It's a great topic, as you were soon to see. This is the first time we've had a repeat seminar, but it occurred to me that since 1999, more than half of us are gone. So half of us are new, so half of you have a statistically valid chance of never seeing this stuff before. That's kind of cool. This sinister-looking character behind my right shoulder is our featured speaker for today. This is Ed Friedman. He's got a PhD in everything from someplace like Detroit. I don't know. And I first met him back in Tech 2, 8 or 9 years ago, when he got stuck with managing the Space Interferometry mission proposal. And I picked up two quirky habits from him at that time. Some of you may remember or have been around me will have noticed that once in a while I make this weird sound. And the other thing is particularly in the morning, at random times, I'm likely to say, well, it's 8:30 somewhere, let's get this meeting started. That's how we started all the SIM proposal meetings at 8:30, was the opening line. So already I've been corrupted, and I've only known him for a few years. And then the final thing is, one of the things about writing my seminar notices, which I've commented on before, is once in a while I just get running on fumes, because I'm in a hurry. I pull something up out of the memory stack, and it's been a little corrupted. And I missed the fact that Einstein's theory of general relativity was written in 1915, not 1905. And I don't suppose more than 75 or 80 of you pounced on me for that. Thank you for the attention. I appreciate that very much. Now, the last thing you should know is we're running off of his laptop, which is a, are you running in Word or some kind of...
I'm using, I'll talk about it
okay.
when I...
But we're fighting the operating system and the battery memory saver. So if the screen goes dark, it doesn't mean you died or having a coronary or something. It just means we got to get the computer fixed. So you're on, Ed. Go.
Thanks. Yeah, I'm using OpenOffice to do this presentation. Some of you may know about OpenOffice. It's my little way of sticking it to the man. That's on there.
Did anybody hear in the back?
Everybody knows who the man is.
Can you hear him in the back, too?
Any reception in the back is good, 5x5 or whatever it is. Thanks. Hey, there's Greg Kopp.
Presumably OpenOffice running under Linux?
We can talk about that. Okay. Well, Bob set the stage here. I first gave this talk in '99, and it has kind of an interesting history. Many people who work at Ball are busy all the time and always interested in a lot of things. And I was always interested in this topic, but never had time to deal with it until I was caught in a hurricane. Harold Reitzema was there. We got stuck in a hurricane in Boston, and everything was shut down. Couldn't get out of Boston, but I was staying in the vicinity of MIT, and I was able to go to the MIT library and to the MIT bookstore, and you'll see why that plays a role in, for me, uncovering this little mystery. So let's go to the next slide. You saw the announcement that in the announcement Bob wrote, that what I'm going to talk today about is a kind of an intriguing thing that's happened. It's the only case I know of where no new science has been uncovered, but a whole new way of thinking about something has come forward, particularly in educating young people who are taking classes in relativity. So when I give this talk, I want to ask, if you're over 45 and you took relativity classes, could you raise your hand? So that's not many. How about under 45 and took relativity classes? Most of the people here. So you can leave. Because the young people...
How about over 50 and got thrown out of college? Why would that happen?
Yeah, I think we know. But the young people will not be surprised by what I'm going to say. So this talk is one that I can't keep giving because the numbers of people who were taught relativity the wrong way are gradually dying out. So let's give me another line. So I want to talk about three things. We may not get through all three. I really want to concentrate on this mass and relativity issue. The next line shows Lorentz contraction. I hope we can get to that. The third one, energy production in fission processes, which was mistaught when I was a kid, I may not get to. And let's go to the next line. So here's my Warning to you, I'm going to just tell you what I've discovered by reading the literature. I'm not, and I'll debate it with you some other time. We're working on 2 proposals that have to be done this afternoon. So this is a welcome interlude for me, because what's going on in my building is crazy. So let's do the mass and relativity thing. And let's go to the next slide. When you take classical physics, you're taught that there are lots of work has been done, and actually some very, very sophisticated experiments to confirm that mass and relativistic mass and inertial mass, gravitational mass and inertial mass have been confirmed to be the same to within 1 part in 10 to the 12th or something like that. Let's go to the next line. And we learned that in classical physics, when you accelerate something, the force and the acceleration are parallel. They're vectors and they're related by a scalar. And everybody knows this, F equals ma. So the inertia of a body is only dependent on its own properties, not the environment around it doesn't influence how it reacts to forces. I don't know why it does that. I couldn't make it stop doing that. Now, this is where the old folks will get kind of, energized. Oh, I remember that. This is the so-called relativistic mass, which is related to the so-called rest mass, and then this equation that compares the velocity of the object in the frame in which you're observing it to the speed of light. And this is one of the standard things that relativity students see. And so that's why I asked about your age. Now, let's go to the next. So we learned that, this is not Bob's fault, this is my fault.
Okay, we're not getting it.
Just, okay, just, all right, everything's fine, we're good.
I should go to college.
We got that.
Yeah, here we go, here we go. Here we go.
Okay, so we learned from this that the mass is a property of the stuff we're talking about in its own rest frame and its motion. So suddenly we've introduced something very different from classical physics, that the velocity of an object and its mass together determine the mass in a particular frame. So let's go to the next slide. And I want to remind you of a couple of other things. One is that everybody knows about E equals mc squared, but the real equation, the energy of a particle, is related to its mass-related energy, which is, you see, E squared equals m squared c squared to the 4th. So E equals mc squared, but it also includes this momentum term. And, sorry, my phone is actually off, but the little thing that says I'm supposed to be giving a lecture was ringing. So there's a couple of different ways of presenting energy in a relativistic sense. And here's really an important thing, is that the relativistic momentum, and I've only written it in a simple way, we could talk about the more the 4-vector momentum approach later, but the momentum kind of looks like the classical momentum, mv, mass times velocity, and it has that, it's okay, just tickle that.
I think I love you.
There you go. All right, well, we're on the next slide. And the next slide, and now we're going to get into where I was first exposed to this. And that is that, remember in classical physics, the force and the acceleration are parallel. They're related by a scalar, so they're just the same vector with a different magnitudes, but it's different in relativity. And the way we do this calculation is to remember that force equals the rate of change of momentum. And here we've already agreed that the momentum is that gamma, which I've put here so we won't forget. It's 1 over the square root of 1 minus v squared over c squared. And if you do a little algebra here, just say cancel.
What do you say, cancel?
Click, yeah, okay, cancel. We do a little algebra,
I'm just saying it.
and right here, this is really critical, that the acceleration of the body isn't parallel to the force. It's the force minus the velocity, which is a vector, over the speed of light. And then there's a dot product between the force and the velocity. And this all gets divided by gamma m. So this is very different than the experience you have in classical physics where force and acceleration are parallel. Here the acceleration is related to the force, a vector, and the velocity, a vector. Bob, let's jump to the next chart. So let's take a look at this again. Here, I've just repeated it so we won't forget. And click it again there, Bob. So what we get is if you do this arithmetic, and if you know how to do dot products, which is just these two values with a cosine between them, if the force and the velocity are perpendicular, then you get acceleration is parallel to the force, and you get this so-called diluted mass. And this is the term that we're talking about today. This is the central issue in this lecture, that when you just consider the special case where the force and the velocity are perpendicular, then the mass that's involved, the inertia that's involved, is almost always in the older books associated with gamma, 1 over the root of 1 minus v squared over c squared, times the rest mass. So let's go to the next line. What's usually forgotten is that if the force and the velocity are parallel, you get a very different answer. You don't get this, which is so recognizable for people, older people who took physics and relativity. You get this. This is always a surprise to see this, that the relation between acceleration and force goes as the cube of 1 over the square root of 1 minus v squared over c squared. So the mass you get from accelerating a body by pushing along its velocity vector is different than the mass you get when the inertia, the ability to accelerate the particle. It's different for parallel force and velocity than it is when they're perpendicular. So now we have inertial properties that depend on the externalities of the system. What forces are being applied and in what direction and relative to the velocity. So the older books cheated. I have a book from the dates back 1962 or something by Iceberg, a book on modern physics, and he says, he has a whole chapter on relativistic dynamics, and he uses this curve to prove that mass increases with velocity by this formula. The mass equals the rest mass divided by 1 minus v squared over c squared square root. And here's this actual data taken over actually several decades. There's some crosses here and some dots. And this is an interesting experiment. It's I call it a television experiment. A beam of electrons goes through a capacitive plate, and they watch the amount of deflection that's achieved as a function of the energy of the electrons. And as the velocity of the electrons increases, the deflection confirms, according to this, that the mass has increased according to this formula. And then they conclude, this is at the end of a chapter, and it says, therefore, we know from experimentation that this formula for mass increase with velocity must be true because it's confirmed. But what they don't mention is when you do the television experiment, the force is perpendicular to the velocity. So this formula works fine, but this experiment does not deal with the other cases where the force and the velocity can have any orientation. That's why I say that there's some cheating going on here. They conveniently left out the other cases, like the special case where the force and the velocity are parallel and the mass increases with a cube of this root down there. So this is what I just said. So let's jump to the next slide. So just to reiterate, in the old way of teaching relativity, this is what was taught, that the inertia was equal to the so-called rest mass of the object times this dilation factor, 1 minus v squared over c squared square root. But they conveniently forgot about this and all of the other infinite possible orientations between force and velocity. Here it's written in a sort of a scalar form where you have the cosine. So it's a little more complicated than what I was taught. I graduated in 1966 and was thoroughly infected with the old way of thinking until, let's go to the next chart. So, I mean, I kind of graphed this out. As the force and velocity change orientation, the inertia of the object as a function of its velocity in a rest frame is a kind of a complicated thing. But that's never discussed in the old books. So the poor sappy student has no way to defend himself in the old strategy because you have 5 different kinds of mass. You have the rest mass, that is the mass in the frame of the object. You have the relativistic mass, that's the terminology that was used, which is the rest mass times the dilation factor that depends on velocity. We have, now we recognize that, and a few people, I guess, knew this, that the longitudinal mass, which is the inertia associated with force and velocity being parallel, that was yet another thing. And we had the transverse mass, that's the inertia associated with the television experiment. And then, of course, you have gravitational mass, which, to really talk about that, you have to do general relativity. So this list was a murky thing to deal with back in the old days, and it's all different now. Books published after about 1993, as I will show you, have solved this problem by asserting with good evidence that all of these are nonsense, except an object has mass in its rest frame, and that's the only mass that we are allowed to talk about. There's no dilation of the mass. Mass is invariant from frame to frame. So that's sort of the central theme of this talk. The old style of teaching, before the late 1989, 90, somewhere in there, the old style that had all these different interpretations was confusing and misleading. The modern interpretation is objects have the same mass in all frames. Well, let me make a little diversion here. I've been using the term frame, and I'm not sure everybody appreciates it. If you haven't taken a relativity course, what they mean by rest frames is observers who are traveling at constant velocity observe events and objects in other frames. And the typical thing to talk about is trains. If you're standing on the station and a train car goes by and you can peer in the window of the train car as it goes by, the activity and the events going on in the car are in a rest frame. Do we have a bucket of water that I can drop this into?
Battery.
Yeah, I could.
I got a sledgehammer.
I could give it to Bob and he would break it.
Creatively.
So frames just refer to the coordinate system that you're in, or a frame might refer to a coordinate system you're observing from your rest frame. So today it's taught that inertia increases by a relativistic factor that depends on the properties of the body and the magnitude and direction of the forces. So if we have force parallel to velocity, we get this cube. If we have it perpendicular, we don't get the cube. And here's a great quote. I'm going to read this to you because I enjoy reading this. This is from a terrific book. If you're a student of relativity, you need to have this book and read it, by Ed Taylor, who's a great teacher of relativity, and John Wheeler, who was Richard Feynman's PhD advisor and is still alive. Extraordinary thing. And they say in one of the later editions of Space-Time Physics, ouch, the concept of relativistic mass is subject to misunderstanding. That's why we don't use it. First, it applies the name mass belonging to the magnitude of a 4 vector, we don't have time to talk about that today, to a very different concept, which is the time component of a 4 vector. So you'll have lunch with me and we'll talk about it. Second, it makes
It's got to make sense to you. You're in marketing. Everything makes sense to you.
So am I.
Oh, right.
Second, it makes increase of energy of an object with velocity or momentum appear to be connected with some change in the internal structure of the object. Not true. In reality, the increase of energy with velocity originates not in the object, but in the geometric properties of space-time itself. This is the... It's okay, we're done with that slide. So let's run the text on. So here in '87, in the American Journal of Physics, which is a journal for physics teachers, you see these quotes: relativistic mass turmoil, unless one goes all the way and introduces MT, that's the transverse mass, and ML, the longitudinal mass, in addition to M, you are actually tricking the students into believing they understand what's going on. That's why I said there's a transverse inertia, there's a longitudinal inertia, and unless you reveal to the student that they, as they didn't do in Iceberg's book that I used in the early 60s, the inertia in different directions under different conditions are different. But the mass isn't changing. So let's move on. Therefore, the faster a particle goes, the more resistant to acceleration it becomes, but the mass hasn't changed. Other things are happening. Energy is being invested in the space-time structure in the frame in which that mass is moving. Okay. This is kind of unfair, but it's important historically. Lev Oken started this whole thing back in 1989. He wrote a paper in Physics Today, a journal for the physics community, and he challenged the physics community, particularly teachers, to reassess how they were teaching the concept of mass. The paper is called The Concept of Mass. And he introduced this whole thing, and it's really interesting, and I'll show you the result of the impact he had by bringing this up on publishers, authors, professors, and students. So he has this quiz, and it's interesting because he's quoting directly from Einstein's early popularization of relativity for the public. And he said, which of these is the right way to express the relationship of the energy of an object to its mass? And you see he's got 4 different cases here. He's using 0 to mean the rest mass, or the rest energy. That is the energy in the frame in which the object is still. So let's go to the next page, and we have, I just said that, so we have the right answer is the rest energy is equal to the mass of the object times the speed of light squared. This one that says the energy equals the mass times the speed of light squared, if you were trained in relativity, you would say, well, the mass increases with velocity, so the energy increases with velocity, and this sort of implies the mass has to change for the energy to change, which is not true. And then you have this. This is kind of correct. The rest energy and the rest mass are related by the speed of light squared. That's okay, but it's still a little ambiguous compared to this much better approach. And finally, this says the energy is equal to the rest mass times the speed of light squared, which means the energy could never change. This is the preferred way to say it, and it's preferable because we only have m, the mass. There's only one mass. It's like Earth. There's an Earth. We live on it. It's the only one we know about. There's no relativistic mass. Oken's idea is, well, first of all, he quotes from Einstein. This is kind of revealing. And you notice that this is a quote from 1948, not too much before Iceberg wrote the book that I read as a student. And this is pretty clear from the man himself. It is not good to introduce the concept of mass, and here he's got the little equation of a moving body for which no clear definition can be given. It's better to introduce no other mass concept than the rest mass. Well, that's a little sloppy too, because that means that there's a rest mass, there might be other kinds of masses. But Einstein himself had dealt with this, and by the way, this is 45 or some years after the invention of relativity, and in his earlier works, rest mass was a common terminology that he used. So even the master had to go through some re-evaluation of this before he came to this conclusion. Bob is pacing the lecture mic, or the computer is. So, a little more clarification. In a very interesting book, I hope some of you will get a chance to look at, called Scouting Black Holes. It's a book for the serious non-expert on general relativity, just using calculus. And you can do all sorts of really interesting problems. And once again, here's Ed Taylor and John Wheeler. These guys have done a great service because they make this material available to industrious people who have the time to do some calculus, but nothing more exotic than that. And here they say the energy is different in different frames, and the momentum has different values in different frames. However, the values of these two quantities can be used to compute the mass, and the mass always comes out the same. All observers see the same mass. So if you're talking about frames, if you're standing on the station platform and a high-speed train goes by, going half the speed of light or something, and you do some experiment and you witness somehow the energy or momentum of a particle in that moving train, and you use the proper equations from relativity and calculate the mass, you will get exactly the same answer as a person traveling in the train with that bowling ball or rolling pin or whatever it is. That's not what we were taught when I was a student. Let's go on. Everyone agrees on the value of the mass, which simplifies things greatly. This is a great gift. Now let me do my poll again. For those people younger than 40 or so, how much of this is familiar? How much of this is unfamiliar in the sense that you were taught that mass changes with velocity? Young people.
I was taught.
Carter Wright, you're not under 45. So
I just look a hell of a lot older after the program.
Well, so some of this lingers, and I'll show you some statistics in a second about how much of it lingers. Let's go on. And this, I think, is a really interesting graph. This is the graph I generated while I was stuck in the hurricane, when I had a chance to go to the library at MIT and look at dozens and dozens of old physics books, and to the bookstore and look at all the new books. So here we are, 58 and 98. And I haven't updated this since my 99 lecture, but you can see, let me tell you what we're doing here. The question is, does mass dilate with velocity? And then we have a binary possible outcome, yes and no. And I think you can see the density of dots here, each dot represents a book, is much higher up until this point, sort of like 1991, than it is after that time. But more important, I thought it was interesting to look at books that are published in multiple editions. So Halliday and Resnick has been around for a long, long time. And you'll see these are the yellow dots. So back in the 61 edition that I own, they said mass increases with velocity. And that was true again in the 79 and 89. And then they switched in 93. Here's a book I know well by Jerry Marion. I was a student of Jerry Marion's at the University of Maryland in the early 60s. And his book here said mass increases with velocity. And the new edition from 1995 says no. And they have, this book particularly has a very nice discussion, perhaps a half a page, talking about the old way of teaching relativity. And that's why I want to reflect on something I said at the beginning of this lecture about no new physics has happened. And this is the only case I can think of where there's been a dramatic difference in the interpretation of what's happening in relativistic or scientific fact. Even though there's no new science, it's taken 85 years of people thinking about it to decide, we're not teaching that right. Sears, an ancient book, dates back to the late 40s. There's a new edition from the early 90s, and they switched. But I think you can see the predominant advice to students is mass does not change with velocity. The mass is the same in all relativistic frames.
Was it just being taught to students incorrectly, or were
No.
practitioners of relativity?
Oh, I'm so glad you asked that. There is a paper in Science Magazine from 2003 about an astrophysics article